Hello and welcome to Sean White's Solar and Energy Storage Podcast. This is part 3 of Energy Storage Systems in the NEC featuring Bill Brooks and myself, Sean White. And some of the things that we're going to talk about here are the energy storage system codes with emphasis on the National Electrical Code and standalone and anti-islanding operations. Be sure to get Sean and Bill's latest book, which is the third edition of PV and the NEC, based on the 2023 National Electrical Code. And by the way, this podcast was recorded in 2021. If you want to find out where to check out the National Electrical Code or what version your state is on or your jurisdiction, you can go to solarsean.com. That's solar, SEAN.com. Find out tons of links, how to find out more about everything. Now it is time to go with the flow. Check it out.
Flow batteries. So they're not that popular, but who knows what's going to happen in the next 3 years. And you're using pumps to move electrolyte. And there's a lot of similarities between flow batteries and fuel cells, kind of how they work. And it directs us to Article 692 fuel cell systems. So we can use 692 if we're going to be using flow batteries. You might not see the flow batteries that much on residential, but you might very well see them on larger systems if you're inspecting a larger system. Flow batteries, you need to name the electrolyte, put it on a sign, what kind of electrolyte you have. I noticed that a lot of the electrolytes are not very toxic. I mean, you look at like lead batteries and all that, you got zinc in there. It's like medicine, things like that. Even with lithium batteries, it's like, that's a medicine, all these different things.
Sulfuric acid is a common electrolyte in flow batteries. There's some similarities there with flooded lead acid batteries.
Mm-hmm. All right. But they have other ones too that you don't have to use sulfuric acid. Just talk about the controls. It's sort of like you get into plumbing with a flow battery, be able to turn them off and things with valves and all that.
As a constantly replenishing battery, so like a lead acid battery, we deplete the process from full charge down to low charge, whatever, and then we have to turn around and charge it back up again. In this case, we've got a large supply of electrolyte. It's like having an extra gas tank. We're just continuing to run that through the process, and then we reverse that process in the charging process. It's interesting technology, and we hope, I certainly hope that it becomes more and more refined, but the problems have all been in seals and pumps and all those things because we're dealing with things that are fairly corrosive. That definitely makes it challenging for these things to last a long time. And so there's a fair amount of maintenance. And so part of it is getting a handle on what the maintenance is and how it's done, try to make it as simple as possible, as inexpensive as possible, as quick as possible. And those things are being worked on. But compared to the very simple battery technologies that we have, lithium ion with cells and lead acid, those are much easier from a maintenance point of view.
Yeah, it's kind of just sloppy like solar thermal or something, all these different tanks and valves and corrosion and all that kind of stuff. So. And so the solid state things just tend to work better. With other types of energy storage systems, it's kind of a free market to, what you want to use, but you got to apply the code somehow. But we don't have special things in Article 706 for flywheels or anything like that. You just use the code as well as you can. 710, formerly 690.10, and that's for standalone systems. And so it's very short. I think it's about a half a page in the NEC. Standalone systems also cover systems like your regular system that can operate in standalone mode. So when you've got grid tie with battery backup, you got to apply this. There's a lot of places in the world, well, like Germany, for instance, where they have a lot of energy storage systems on houses and they don't have standalone mode. There's also these things called virtual power plants too, where they'll coordinate a whole bunch of standalone residential batteries and compete with power plants. So if you were going to use equipment for standalone system, it needs to be listed as standalone because it wouldn't work otherwise. And so you can't buy your PV equipment at the auto parts store anymore. Dang it. For a standalone system, you need a permanent plaque or directory, each service equipment location, or at an approved readily visible location.
This is similar language in Article 705.10. And in fact, in the 2023 code, just to keep these things from diverging from each other, we're just making a reference back to 705.10. The whole idea is that if we've got multiple power sources, we identify them. Now, the reality is we may not have a service equipment on a standalone system. So if we don't have service equipment because we don't have a utility service, readily visible location means that's something that would be approved by the authority having jurisdiction, you folks. So if somebody has an off-grid house somewhere, wherever is the most logical place to identify something, that would be something to work out with the installer or the homeowner to say, okay, if somebody were to come up to the house and there was some problem, let's say there's a fire or something, where would they go to turn this stuff off? And how would you tell them how to get there and come up with something that makes sense?
Power supply can have less capacity than the calculated load. So we don't need to be able to supply the whole calculated load. And the power supply shall be at least as much as the largest load. And some people used to take this as like, oh, the inverter has to be at least as much as the largest load. But it could also be a generator or a generator plus an inverter. All you have to do is be as big as your largest load. So it's possible that somebody could have a huge load that's bigger than what their solar inverter can handle, but it only works when the generator is turned on. A lot of people that are living off grid, they know that they can't vacuum and have the refrigerator running at the same time.
They need a bigger inverter.
Yeah, they need a bigger inverter.
But they're not required to. That's the important thing, is that if you want to live that way, have on at it. And again, these are standalone systems. One of the points he's making here is that you can't connect a 10 kilowatt load to a 5 kilowatt inverter, because every time that 10 kilowatt load would come on, it would turn off the inverter, and that would be stupid. At the same time, you can not turn on the 10 kilowatt load. And so one of the things that we're adding to the 2023 code, which is very common in standalone systems, is manual load control. What's manual load control? I don't turn stuff on when I'm in standalone mode. So there's a lot of things that I'm not going to run. I'm not going to run my air conditioner in standalone mode. I'm not going to run my pool heater in standalone mode. There's a lot of things I'm not going to do. And so I can elect to do that manually, or I could have an automatic controller that would prevent me from doing that. And so it really comes down to choice. Again, these are generally systems that are optional in nature. They're not required, legally required, or emergency 700 or 701. And so since if they're not under 700 or 701, then it's really just the choice of the customer, whether they want to run the thing or not. What you hook up to it becomes important, and how you keep loads off that you don't want to run is really ultimately up to the owner and their operation.
The standalone source determines the size of the conductor, obviously. So it's like however much your inverter can put out, for instance, would be how big your conductors would be. And then if you had more than an inverter, size it based on your inverter plus your generator sometimes, perhaps. Let's say you have a 100 amp panel board, but your inverter can only put out 50 amps, then you don't have to size your conductors based on 100 amps.
Correct. Yeah, it's based on the power source size, not on the load center size.
This has always been one that was kind of fun to explain. That sometimes what you'll have is a 120 volt inverter, and you're going to use 120, 240 volt designed service equipment. So you get like your regular panel board. Then you bond line 1 to line 2. That works great. The only thing is you have to watch out for is the neutral bus. That you're going to have double the current on the neutral. Instead of on neutral, currents cancel each other out. They add to each other. And so if you have a multi-wire branch circuit, that would be like some Romex with line 1, line 2, neutral, and ground in it. That would be bad because you would start getting too much current on the neutral. So you have to have a sign that says single 120 volt supply, do not connect multi-wire branch circuits. You got to make sure that your neutral bus can handle those extra currents. You're just going to have more on the neutral instead of less.
This came from Article 690. All of 710.15 is basically a cut and paste from 690.10 when it was moved into this new article. And the fact of the matter is, it's very rare, if at all, that you can buy 120 volt distribution equipment. So all the equipment that's on the market is a massive market for 120, 240 equipment, split phase. Rather than only being able to use half of that equipment, these are the rules we came up with to allow you to use the 240 volt equipment and essentially convert it into 120 volt equipment. The only challenge that you have is if you're running loads off of this 120 volt equipment. And as I did in my house, I had several multi-wire branch circuits. I had to convert those multi-wire branch circuits into standard branch circuits, which was actually fairly easy to do, in that you can basically run, as long as you run both phases off the same circuit breaker, then the neutral current is protected as it normally is. So the neutral current is normally protected by reducing the amount of source current that you have from your circuit breaker, whether it's a single pole circuit breaker for 120 volt loads, or it's a split phase system. We're allowed to use a 240 volt circuit breaker and then split those circuits somewhere else, like in a kitchen is commonly done, and they share the same neutral. And because they're on opposite phases, then the neutral current is cancels based on the current. And the worst case is when one phase has all the current and the other phase has no current. But multi-wire circuits are still very commonly used. And if you were to convert a backup panel, for instance, that's where this comes in. You have a backup power supply from an energy storage system, standalone system, then you would convert those multi-wire branch circuits into standard branch circuits by hooking both the hots to the same circuit breaker, the same phase of the circuit breaker, which if you do the same circuit breaker, that would work. And then this just is a warning sign to prevent people from adding multi-wire circuits. You'd have to convert them all to single wire standard circuits.
Yeah, one thing that's kind of interesting is in most of the world, all the electricity coming into a house is just lined to neutral. I would say that probably most service equipment for houses in the world is just lined to neutral, and you wouldn't have this problem. Maybe we could just like get some European or Chinese,
we're just trying to be fancy
service
in the United
equipment.
States
Yeah.
with this split phase.
Yeah, they also kind of almost double the voltage. So they're like 230 volts lined to neutral is pretty common around the world. Direct PV system. So what a direct PV system is it just when you don't have any energy storage, you just have PV connected to a load, and cows like direct PV. So that's probably the most common type of direct PV is pumping water. Sometimes it's a fan, that just like blowing in your roof. It's good to have a direct load. You need more when it's sunny.
Your tank is your battery. In this particular case, the cow's drinking out of the watering hole. That's your tank. That's your battery. So during the day or sunny days, you fill up the tank. And then if you had a really rainy, cloudy weather, well, you're probably not going to need a whole lot of water. And at night, you got the water there in case they get thirsty at night. So that's your tank. And this also applies to folks that are using catchments and other types of systems in Hawaii, where you might want to pump water to a storage tank and use that as a battery, if you will. So if you're on a well pump, a good idea is that when you have excess solar as a diversionary charge controller, kind of what we're talking about, diversionary load is a better way to say it. It's not really a charge controller. We'll just call it a diversion load and say that when our battery gets full in the early afternoon, then we start our water pump up and we run that for a couple hours. And let's say we have a 2,500 gallon tank or a 5,000 gallon tank. We fill that water tank up. We don't have to use our well pump at night or when the electricity is expensive or whatever. So it's just another way to use electricity. So a storage water tank can be a very effective battery, store a lot of energy in there.
Probably like the most not smart type of direct PV system would be direct lighting, because then the sun's out and you don't need the light, right? So,
yeah, it's kind of silly.
If you find somebody doing a direct lighting system, then you better look out for other things too.
Yeah, sounds weird.
So with a backfed circuit breaker for standalone, you need to secure it. So for an interactive inverter, you don't need to secure it because the breaker pops off by accident. You don't have a hot breaker dangling around because the interactive inverter output circuit always anti-islands, so it immediately shuts off like in a pulse of a sine wave or so. But when you have a standalone circuit feeding a panel board, you need to secure it.
Going on to 712. We're going to cover some of 712 here. Just going to give my opinion about 712. There are very few DC microgrids out there. And in the 2023 code, we're migrating all this stuff into Article 705 because we have interconnected power sources that interconnected both on the DC side and the AC side. We've seen the DC coupled battery systems. We showed that earlier, DC coupled PV with energy storage and the like. That really belongs in Article 705 because we do it all the time. DC microgrids are kind of a different animal and can get very, very complex. There's a few industrial applications out there where DC microgrids are being used. They're very uncommon. They are extremely rare. They're like unicorns. And so if you find one, that's really cool. And it would be really interesting to look at them. We want to make it really clear that DC microgrids are unicorns, and we have some very basic language in 712. Not real happy with the language in 712, but it's something to talk about. It's something that's there. And it was really intended as a placeholder to see if that technology ever went anywhere. But to say that my PV system connected to an energy storage system, both operating at 400 volts, going into, say, a solar edge inverter or something like that as a DC microgrid is absolutely false. There's no DC microgrid controller. There's none of that stuff. Do not go into Article 712 for the typical equipment that's on the market today. That's all covered under 705.
I remember there's some winery in California that did a field trip too when the Intersolar conference was here. I think it was halfway done for marketing, just like DC microgrid.
Yeah. And like I said, that would be a unicorn. Hey, it's all unicorn today.
Hey, my daughter sees them all the time.
I'm sure.
Nowadays, we call things functionally grounded instead of ungrounded and grounded like we were before. So if you hear people talking about a grounded inverter or ungrounded inverter, you know they're talking about the 2014 NEC, 99.9% of the time. And so functionally grounded is a system that has a ground reference that is not solidly grounded. Reference grounded system, low resistance electrical reference to ground. So we could say perhaps that is the fuse grounded system, which is also another type of functionally grounded system.
I'd say in most cases, a reference grounded system is actually a resistor grounded system. So some of you may remember SunPower back 10 years ago, their modules had to be positively grounded instead of negatively grounded. And one of the things that they would do with their systems is they would have a nighttime depolarizer, they called it, that would basically connect the system at night to the positive to ground. There's a variety of reasons for doing that, and they would often do that through a resistor and things like that. So that's an example. And there are other types of resistively grounded systems in healthcare and other areas in the AC world that use an impedance ground. If it's an AC system, we're going to call it an impedance ground, whereas if it's DC, we'd call it a resistance ground. But again, those are very rare. That would be a rare occurrence of an awfully rare thing to start with.
DC microgrids over 300 volts shall be reference grounded or functionally grounded. Now that comes the fun part. We like electric vehicle power transfer systems. Right now, it is kind of a unicorn, but it is the future, I believe.
That language, power transfer system, is the 2020 code, is it not?
Correct.
The 2017 code still calls it an electric vehicle charging equipment or charging system, I think. So just so you don't get confused, some of the stuff we're trying to give you some heads up on where the code is going and some of the language where it's going. This has always been related to electric vehicle charging stations and stuff like that. And a really cool part of that is the allowance that you could have. Let's say you ran a 200 amp feeder to a bank of electric vehicle chargers. Well, each charger, let's say, uses 40 amps. Let's say you put 10 chargers on that 200 amp feeder. Normally, in the old code, before 625 came along, you weren't allowed to do that because, shoot, if 10 people plug in, which once electric vehicles started taking off, that was a real option. Now you've got 400 amps worth of load on a 200 amp feeder, and that would be unacceptable. Okay, but Article 625 was groundbreaking in that it brought up the issue of being able to sequence chargers. So now you have a charging controller. The charging controller now looks at, 10 people have plugged in. So once it gets past 5, you're at the limit of what the 200 amp feeder can handle. So now you go 6, 7, 8, 9, or 10 in an electric vehicle charger. Now the sequencer has to kick in. And what does the sequencer do? What it does, it basically chooses which cars to charge. That choice could be made based on whether they were the CEO of the company, and so they get preference. Maybe if they put their card in and they were a special person, they get a better charge rate. Or it could be that they're willing to pay more money, right? So if they're willing to put in more money, then maybe they get more charge. Or if everybody's the same and it's an egalitarian situation, then everybody gets a little bit less. So now if you had 10 vehicles plugged into that same 200 amp feeder, you are now charging those cars at half power instead of full power. So that was a really cool thing, was all based on the charging side of the equation. But then they started realizing, hey, these chargers are now going to become bidirectional. Okay, what does that mean? No, well, it means they can actually source power out of the vehicle into the grid it's not just a charging system, it's a power transfer system. And that's where this language has gone. And we're going to see a lot more of this to come. As Sean points out, there's very little, if any, of this stuff currently in existence because bidirectional charging systems are really only in their, I would call, prototype stages at this point.
Like these car companies, they're trying to just sell as many batteries as they can, and there's sort of a shortage. They can't make them fast enough. So they're putting them in the cars more so. We actually did a calculation, like Bill's car that has essentially the same LG batteries as the LG Chem battery has in it. And it would have cost him the same amount of money to buy as many kilowatt hours to put on his wall as his whole car costs to get the same amount of kilowatt hours.
The car's free.
Yeah, it's like a free car, with all the batteries in that.
Buy a battery and get a car for free.
And then it's kind of funny too. It's like if you have a car, some of them go up to 100 kilowatt hours, and you're driving around with 100 kilowatt hours, and you go home and you have a PV system that's really big, the power goes out, you can't even charge your car. Until you go buy a battery. And what are you going to buy? You could even buy a 10 kilowatt hour battery, and then you could be charging your car. It's kind of silly. So what happened was in Japan, they had that big Fukushima problem over there. And apparently they required the electric vehicles over there, which was mostly the Nissan Leaf back then, to be able to power things when the grid goes down. And so they're doing that, I guess, in Japan, but nobody's doing it here legally. Like if I did it with my car, it automatically voids the warranty if I figured out some way of doing it. But eventually, I think they say that probably Nissan is going to do it first, since they already have the technology. Once they do it, I think everybody's going to do it. I was talking to somebody that worked at Tesla saying that all they have to do is pretty much change the software and that you could do it with your car there too. So,
yeah, the biggest issue is just working out the battery warranty issues. And I think that's very simple and easy to do. But I think it's far more cost effective to drive your battery than it is to stick it on their wall. That's why we're going to see in the future electric vehicles turning into the storage media for a lot of systems, including zero net export projects in Hawaii, especially because of COVID and a lot of people working out of their homes. Now you've got a much larger electrical load at your home and a bigger need for energy storage and for backup power. So now I'm stuck at home working. Not stuck, but I'm doing a lot of work from home. And so why not use my electric vehicle to store my electricity during the afternoon and dissipate some of it at night? I'm not going to take it all the way down to zero, but remember, my battery in my car is 10 times the size of the battery that's on my wall. And so I can afford to cycle that differently and not as deeply and still leave me plenty of supply, particularly in the islands where my typical driving distances are fairly small. I could have plenty of storage for my house and my driving.
It's a battery on wheels. Like have a vacation home with an electric car. The car could be making money for you because you can also assist the grid and support the voltage and the frequency and all that and make that grid a lot cleaner.
We're changing into overcurrent protective devices.
We're going to talk about fault currents. So this is a little intro to the fault currents. This is a new recent thing that we just did and started talking about. And so we've got overcurrent protection devices. And you always think of them as like, oh, there's a 40 amp breaker. But some people might call that a 10,000 amp breaker because there's not just the amp rating, but the interrupt rating. That would be like the most concurrent. So then if you went to 20,000 amps and a 10,000 amp interrupt rating, it might not work. It might catch fire or something like that. There's overcurrents, which is just like 40 amp breaker. An overcurrent would be like 45 amps or just over 40. Go for a long period of time, maybe to heat that breaker enough to make it open the circuit. But then you have fault currents where you're just like, direct short circuit, something like that. And then that would hopefully just pop the breaker, like make it open up really quick. And so let's get into some of this terminology. Ampere interrupting capacity. So it could be in kiloamps or in amps. A lot of times we're talking about kiloamps. So 10,000 amps would be 10 kiloamps. Interrupting capacity, that would be the maximum current that you could interrupt. So it's sort of like the breakers have a range. So it could be 40 amp breaker, it could be between 40 and 10,000. And then maybe you'll have a main breaker on the supply side of that that's going to get those higher amps there. There's short circuit current rating, fault current rating, all this. And so what do you do with all this stuff? Sometimes If you're doing a supply side connection, this could become relevant. Or if, the closer you are to the main breaker, the more relevant it gets. Or you also can have batteries and stuff like that. Available fault current calculator that people use.
Yeah, but it's very straightforward stuff. So if you're interested in learning about available fault current and fault current calculations and all, these little Excel spreadsheet calculators, it'll help you understand when you're at the service equipment, what kind of fault current you may be presented by the utility. Might say that, in residential applications in Hawaii, you never have anything over 10,000 amps. Okay. So that has to do with the transformers they're using and stuff like that. In certain areas with commercial and industrial applications, certainly in Honolulu, you're going to have available fault currents that are well above 10,000 amps. And so the equipment is rated for that. Whatever the initial service equipment was selected based upon what the utility provided as their fault current calculation. If you have the nameplates of the service equipment for either a residence or a commercial building, it's a very good assumption to assume that the available fault current for the facility is no greater than the rating of the service equipment. And once we work off of that rating of the service equipment, we could use this calculator to find out what the fault current would be downstream. In residential applications, especially if you're dealing with smaller conductors like 10 gauge conductors or 12 gauge conductors, you'll find that your fault currents, even going from 22,000 amps, drop like a rock when we go down into those smaller circuits. And so your available fault current, even going to a solar inverter off a 10 gauge or 8 gauge conductor off the service, is dramatically lower than it is right at the service equipment. It's pretty cool stuff if you want to play around with it, but it's also helpful to understand how quickly those fault currents drop.
All right. And so now I think some of that fault currents is going to be relevant over here, because we're going to be talking about interconnected electric power production sources. That's 705. Usually we mostly talk about our line side and our load side connections. And also 705 is the Hollywood Freeway. Microgrid interconnect device, that was like the Tesla gateway. It's a device that allows a microgrid system to separate from and reconnect to a primary power source. Are you able to use that without a power wall? Like, will it connect to something?
You could use it as a switch, yeah. It's just a box and it's got a relay in it.
Tesla has an inverter now that looks like that too. Microgrid system definition, to me, is a little bit weird. Premises wiring system that has generation, energy storage, and loads, or a combination that includes the ability to disconnect from parallel to the primary power source. You might think that, well, it doesn't really work if you're off grid, because we have to have this ability to disconnect from and parallel with the primary power source. But maybe you could just have that ability, but not ever have a primary power source.
Right. That's why it's written that way. And it's been adjusted in the last couple of code cycles. But the whole idea of a microgrid interconnect device is something that disconnects and reconnects, because if you never connected to another source, there would be no reason for a microgrid interconnect device.
And except maybe you could have two microgrids connecting to each other.
You could. 702.
702, just getting back to that. So like if you had automatic transfer equipment, the standby source shall be capable of supplying the full load. So that kind of contradicts what we were talking about. If you had a microgrid interconnect device and a standalone system, then you only have to back up the largest load instead of the full load.
Well, there's two options. One is you have to take the full load or have load management and automatic transfers. Now, load management is going to become very common in the next couple of years. There are several companies that are currently on the market with some pretty expensive load management equipment. That stuff's going to get a lot cheaper and a lot better. A company called Span, everybody thought they were cool, and their stuff is kind of steep. The company that makes lighting stuff, is it Lumen? They make lighting controllers and dimmers and stuff like that. Well, they have their own load management system at Home Depot. You can buy at Home Depot. It's a whole panel board with breakers that are programmable and the whole 9 yards. Pretty cool stuff. And so load management is becoming more and more reasonably priced in the residential market. We've had it in commercial for decades. Energy management systems have been common, but the concept is working its way into residential. Stuff that you would have on your iPhone or whatever, that you'd be able to turn things on and off in your house. And of course, you'd want to have that in a backup power system So you could program what breakers to shut off. So the whole idea here is that in a microgrid, you could basically say, when you go into microgrid mode, instead of having to rewire your whole house, I am going to lock out my electric dryer. I'm going to lock out my electric water heater. I'm going to lock out my air conditioner so that those things don't try to run off of my inverter, because my inverter is not big enough to run all those things in my refrigerator. So I want my refrigerator first, my lighting second, my communications, TV, those things. I want to make sure those things stay up and running, and I don't want to turn them off if somebody decides to run the dryer for some reason, forgetting that the power's out or something like that. That's where we're going to with all this load management. It's not a requirement in Article 705. In fact, we've added a bunch of load management information into Article 705 in the 2023 code. It's a design decision at that point. For optional standby systems, which are different, which are typically transferring to a generator, those systems, according to Article 702, if you're going to use an automatic transfer switch with a generator, then you have to follow either the full load or load management. If you have a manual transfer switch, you're allowed to run that system any way you want. Basically, the idea is that if you're going to manually have to go out and start your generator and turn a switch, you can also manually turn off circuit breakers in your house, and that's fully permitted in Article 702. So there you go.
Time to switch it up, and thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more, go to solarsean.com. That's solar, SEAN.com. And by the way, Bill's website is brooksolar.com. That's one S between the Brooks and the Solar. And you can also find out more about classes on HeatSpring with these guys. And when I say these guys, I include myself, Sean and Bill. And here we have heatspring.com/SEAN. Check it out.